Hi everyone, welcome to my channel. In this video, we will see Norton's theorem for DC circuits. In the previous video, we have seen the Thevenin theorem for DC and AC circuits and some solved problems on the Thevenin theorem for both AC and DC circuits. In this video, we are going to see the Norton theorem for DC circuits. We will see the statement first. So, in any linear bilateral network consisting of active and passive elements can be replaced by an equivalent circuit consisting of a single current source in parallel with a single resistance. This current source is called as Norton's current and the resistance is called as Norton's resistance. And the corresponding equivalent circuits are shown in the figure here. So, this is a linear bilateral network connected to a load of resistance RL. Upon connecting this, a load current IL is flowing in the load. So this entire network can be replaced by a single current source with a parallel resistance. So with load resistance as it is. So this equivalent circuit is called as Norton's equivalent circuit. That is the current source is there. That is, this current source is called as Norton's current. So and the resistance is called as Norton's resistance. So these two should be calculated. We have some procedure for that for the calculation of Norton's current and Norton's resistance. We will see the steps to calculate these two. So steps to determine Norton's current and Norton resistance. The first step is replace the load resistance with a short circuit. So in the given problem, he asked to find the current across some element. Some resistor, so we have to treat that resistance as a load resistance, and according to this we have to remove that load resistance and we have to keep a short circuit across that load resistance. So after keeping the short circuit, we have to find out the current in that short circuit. So this short circuit current is called as Norton's current, so that is designated with IN. So this is the way to calculate Norton's current, a very simple step. So the short circuit current is also called as Norton's current. Now we will see how to find the Norton's resistance. So to find the Norton's resistance, first we have to remove the load resistance to form an open circuit. So and then we have to deactivate all the sources in the network. So the deactivation procedure is same that of Thevenin theorem also. So that means if voltage source is there, we have to make it as a short circuit. If current source is there, we have to make it as a open circuit. So then after deactivating all the sources, we have to calculate the resistance from the open circuit end. So this resistance is called as a Norton's resistance, Rn. So if you observe the procedure for calculation of resistance, that is Norton resistance, and the procedure for calculation of Thevenin resistance is both same, and also the values of Thevenin resistance and the values of Norton resistance also same. So upon calculation of these two, Norton's current and Norton's resistance, we have to draw the equivalent circuit. So as shown in the figure, so Norton's current in parallel with the Norton resistance connected to a load resistance RL. So now in the problem generally he asked to find out the current in the load resistance. So the current in the load IL can be calculated by the current division rule. So I think all of you know about the current division rule. If you don't know about the current division rule, the link is there in the description, so please go through it. So the current, according to the current division rule, IL can be calculated as the total current is multiplied with opposite resistance, that is Rn, by sum of the two resistances, that is Rn plus RL. So this is the way to calculate the load current from the given equivalent network. So we will see an example so to understand betterly. So find the current through the branch AB by Norton's theorem. So if you observe here, so here the branch AB that is connected with a 15 ohm resistor. So we have to treat this 15 ohm resistor as a load resistance. So he asked to find the current in the 15 ohm resistance by using Norton's theorem. Therefore, we already know the steps for Norton's theorem. So to calculate Norton's current and Norton resistance, we have the steps that is mentioned in the previous slide. So first we are calculating the Norton's current. So to calculate the Norton's current, we have to replace this 15 ohm resistance with a short circuit. So that is shown in the figure, and we have to redraw the circuit. So after making the short circuit, the terminals A and B. So here we have a two loops are there from the given network. So one is this loop, other one is this loop. So let the currents in the two loops are I1 and I2. So therefore the short circuit current ISC is nothing but the summation of the two currents I1 plus I2. So to calculate where I1 is nothing but 12 by 2, that is 6 amperes, and similarly the I2 current is nothing but minus 8 by 5, that is minus 1.6 amperes. Therefore the short circuit current is the summation of the two currents I1 and I2. Therefore ISC is equal to 4.4 amperes. So we know that the short circuit current is also called as Norton's current, that is 4.4 amperes. So after calculation of this Norton's current, we have to calculate the Norton resistance. To calculate the Norton resistance, first we have to remove the load to form an open circuit, and the equivalent circuit is shown in this figure. See here we have a load resistance, that is 15 ohm resistor is removed, so that open circuit is formed between the terminals A and B. Now we have to calculate the Norton resistance between the two terminals A and B, that is Rn. So and also the second step is we have to deactivate all the sources in the given network. So here we have one voltage source is there, so two voltage sources are there. So we have to these two voltage sources should be short circuited, so that is shown in the figure. So since 10 ohm resistor is connected with a short circuit parallel, therefore there is no current flowing in the 10 ohm resistance, therefore this resistance is ignored. And again, so now if you calculate the equivalent resistance between the two terminals A and B, with respect to terminals A and B, this 2 ohms and 4 plus 1 5 ohms both are in parallel. Therefore the Norton resistance Rn is calculated as 1.43 ohms. Upon calculation of Norton's current and Norton resistance, we have to draw the equivalent circuit, that is Norton's current source. Current source is parallel with a resistance, Norton resistance, and connected by a load resistance, that is 15 ohm. Since in the problem he asked to calculate the current in the 15 ohm resistor, so that 15 ohm is a load resistance. Therefore the current in the 15 ohm is nothing but load current, that can be calculated by the current division rule. IL is equal to the total current multiplied with the opposite resistance for 15 is 1.43. So by sum of the two resistance, so that the current in the load is 0.383 amperes. Thank you.